Hello everyone, welcome to Thermodynamics Lesson 12. Here we will be covering a dual cycle. A dual cycle is a combination of the Otto cycle and the diesel cycle. This type of cycle is used as an alternative engine type for cars and trucks. And so we will now be covering, well, how do you analyze a dual cycle? Well, first let's explain the attributes. So processes 1 to 2 is adiabatic compression. 3 to 4 is isochloric. 3 to 4, no, I'm sorry, 2 to 3, not 3 to 4, 2 to 3. 3 to 4 is isobaric. And then heat is added, by the way, from 2 to 3 and 3 to 4. 4 to 5 is adiabatic. And 5 to 1 is isochloric again. So what is going on in each stage? Well, we can show you later on with all the math, but I'm just going to tell you first off right now. 1 to 2, the piston is compressing the air and fuel mixture. 2 to 3, heat is added through an igniter, and 3 to 4, the gas is pressurized even more and ignites further, so heat is added from 2 to 3 and 3 to 4. And then from 3 to 4, the piston starts moving backwards, and in 4 to 5, the piston starts moving backwards more, and that's where the work output is. So, well, since this is a combination of a dual or of an Otto and diesel cycle, you are also going to have a compression ratio, except this time you're going to have a compression ratio here. One sec. Ratio. Except instead of a cutoff ratio this time, you are now going to have a volume ratio. Which is going to just be VR, and which is going to be equal to V4 over V3, which is still actually the cutoff ratio. So volume ratio, cutoff ratio still exists. And yeah, R is equal to V3 over V2. Now here's the specific thing about dual cycles. In my book that I was doing it off of, they did not refer to this as a cutoff ratio. They refer to it as simply the volume ratio. They'll say the volume ratio for the isobaric section is this. They didn't call it the cutoff ratio. While in diesel cycles, they will call it the cutoff ratio. I do not know what type of textbook you are using. As a result, I do not know what type of term they will be placed. But from looking at the specific ratios for both cycles, if it's a volume ratio or cutoff ratio, my belief is they will be pointing to the same thing. I am unsure if cutoff ratio is specifically for diesel, but I highly doubt that based off since it's a dual cycle. But just keep that in mind, terminology might change from book to book. Alright, so and now let's get into the fun part, or the engineer part, the analysis of this cycle. Well, it's a closed system because it's an Otto and diesel cycle combined. Otto and diesel are both closed system. It's not going to suddenly become open system, so we analyze it like a closed system. So first law we're using is the delta U is equal to Q minus W. Now the efficiency, as always, is equal to the work of the cycle divided by Q in. So this can be changed as the work of the cycle over M is equal to the Q 2,3 over M plus Q3,4 over M, because recall, heat is being added from 2 to 3 and 3 to 4. So this becomes, remember, work of the cycle can be written as all the heat in, so Q23 plus Q34, minus the heat out, which the heat rejection is only in 5 to 1, over Q2 Q23 plus Q34. Sorry, I don't know why my writing is so bad right now. I'm going to try and make it better for you. So then the efficiency can be written as 1 minus Q51 over Q23 plus Q34. Now, let's break this up. So, process 5 to 1 is isochloric. Since it's isochloric, that means there is no work done. That means the change in internal energy is equal to the heat of that, or the Q of that section. So that'd be 1 minus U5 minus U1. Now, Q23 is also isochloric. Therefore, no work, change in internal energy is equal to the heat of that state, which is, or that process part. So Q23 can be written as U3 minus U2. And then if you recall from the previous video on diesel cycles, the heat for the isobaric part can be written as the change in enthalpies of those sections, so H4 minus H3. Now you might be wondering, well, John, what about the individual states and how to break them up into different parts of equations? Well, this is lesson 12, so I'm not going to cover how to do each individual state. In addition, lessons 10 and 11 both went into how to analyze an Otto cycle and how to analyze a diesel cycle. So on a closed system, we should be able to now analyze each individual state based off the first law. So I'm not going to break down each state again in this video. What I will do, however, is I'm going to do an example problem on a dual cycle. However, for this problem again, I will not be providing a data sheet for like where I'm getting my values from. I am getting them from the Moran-Shapiro Thermodynamics Fundamentals 8th edition, table A22. This is where I'm getting my values from. It's the metric version of the ideal gas air table. I do not want to spend as much time going through the table because at this point we should know how to read a table. At the same time, having to go through and find each value takes away time that can be used covering the problem. So I already saw this problem before. I'm going to explain to you, and I have looked up each of the values out of the table. Some are estimations because sometimes I didn't interpolate if values were specifically close. So keep in mind if it's a little bit off. So I will come back to you once I have copied down the problem. Thank you. Welcome back. Well, here is an example for a dual cycle. So what do we know? What is it given to us? Well, working with the air standard dual cycle, we are given a compression ratio of 18, which I forgot to write down. We're given the starting pressure and temperature of 300 Kelvin and 0.1 megapascals. Pressure ratio for isochloric section is 1.5 to 1, which means P3 is 1.5 P2. And the volume ratio for the isobaric section is 1.2, which means V4 is 1.2 times as much as V3. What do we want to do? Well, we need to determine the thermal efficiency and the mean effective pressure. Cool. Well, if you recall, mean effective pressure, we need to know the work of the cycle, and the efficiency, we need to know the U5, basically the internal energy, specific internal energy of most of the states, and the enthalpy of H4 and H3. So let's get to work. Let's do that. So, well, to do that, first we have to analyze what is going on at each state point. So let's start out with state point 1. By the way, thermodynamics, before you're doing anything related to a cycle, unless it specifically tells you, like it's a diesel cycle, it's an Otto cycle, and you're operating at cold air standard, and you just have to find thermal efficiency, you're going to be calculating all your values at each individual state point, no matter what it is. I remember in one of my exams, we dealt with open feed water heating and cold feed water heating. The problem I gave you was a problem we had on our exam. Well, not specifically, they're all the same. Was like a problem we had in our exam. And before we could even do anything, you have to find the values at each individual state point. So, state point 1, dual cycle, let's go. Well, it's given to us. T1 is 300 Kelvin, P1 is 0.1 megapascals. We go off the chart. U1 is equal to 214.07 kilojoules per kilogram. VR is equal to 621.2. That seems very high. That seems exceptionally high. Am I sure that's right? One moment. Yeah, okay, that is correct, I guess. Okay. State point 2. All right. So state point 2. V1 over V2 is equal to VR1 over VR2. So VR1 is equal to 18 over VR2. VR2 is equal to VR1 over 18, which is equal to 34.5. From that, we get T2 is about 898 Kelvin. U2 is about 674 kilojoules per kilogram. And H2 is about 931 kilojoules per kilogram. All right, and we'll need the pressure. So P2 is equal to P1 T2 over T1 V1 over V2, which is equal to 0.1 megapascals times 898 Kelvin over 300 Kelvin times 18, which is 5.39 megapascals. All right, state point 3. Isochloric, so work is equal to 0, and V2 is equal to V3, so V2R is equal to VR3. P3 is equal to 1.5 P2, so P2 over T2 is equal to P3 over T3. So then we get T3 is equal to P3 over P2 times T2, which gets 1.5 T2, which gets 1342 or 47.5 Kelvin. Go to table. We know H3 is equal to 1452 kilojoules per kilogram, and U3 is equal to 1065 kilojoules per kilogram. All right. What's next? State point 4. State point 4. Well, same pressure, so P3 equals P4. V3 over T3 is equal to V4 over T4. T4 over T3 is equal to V4 over V3, which we know is 1.2 because we're given that in the problem. So T4 is equal to 1.2 T3, which is equal to 1617 Kelvin. Go to our air table, we get that H4 is equal to 1778 kilojoules per kilogram, and VR4 is equal to 5.609. State point 5. State point 5. So V5 equals V1. Remember, it's isochloric. So V5 over V4 is equal to V5 over V3, which is V3 over V4, and V3 is equal to V2. So this basically becomes V1 over V2 times V3 over V4, which is equal to 18 over 1.2, which is equal to 15. So VR5 is equal to 15 times VR4, which is equal to 84.135. So at this point, we don't really care about the temperature. So U5 is 475.96 kilojoules per kilogram. I know that was fast, so I'll do a quick recap. So state point 1 was given with the temperature and pressure. We go to our air table, we look up our internal energy and our reduced volume, and we get these two values. State point 2, well, we need to find what VR2 is so we can go to the table and get our values. Well, we get our values here by just doing volume ratios of V1 to V2 and VR1 to VR2. On that, we're given VR2, go to the table. It's really, really close to one of the temperatures, but you can still interpolate if you want to be really, really accurate. And you can get these values here. We then need to know the pressure of P2 because we need the pressure for P3. So we then find P2 using ideal gas law, and we get 5.39 megapascals. State point 3, find what P3 is because P3 is 1.5 P2. So we use ideal, and then we use the ideal gas law to find temperature at state point 3, where we can get all of the values. State point 4, isobaric, same thing as before, ideal gas law, find T4, look at the table, get your enthalpy values, which you need for the efficiency equation here. State point 5, rinse and repeat. So now that we have all the state points analyzed, we can now actually do what the problem wants us to do. Find the thermal efficiency. Well, the thermal efficiency is equal to 1 minus, if you go up here and you rewrite this equation here, 1 minus U5 minus U1 all over U3 minus U2 plus H4 minus H3. Plug everything in, you get the efficiency is equal to 1 minus 475 minus, 1 second, sorry, I can't even read my own writing. Okay, minus 214 all over 1065.8 minus 673 plus 1778.3 is 1452, and you get 0.635, which is 63.5% efficient. Part B, the mean effective pressure. Well, again, mean effective pressure is equal to the work of the cycle divided by the mass all over specific volume at state point 1 times 1 minus 1 over R. So we need the work of the cycle, yay, which is equal to U1 minus U2 plus H4 minus H3 minus, H3 minus U5 minus U1 from here. Time, oh wow. Yeah, wow, I forgot this actually requires a lot of conversions because we need to know the specific mass. Well, guess what? We found it in our previous video, and since these are the exact same values, if you don't mind, I'm just going to write out what the specific mass is with everything. So it's going to be mean effective pressure, that is the eraser. If you want to actually have it solved again, the last 3 minutes of the previous video on diesel cycles, I go over how to find V1, but this is just a repeat of that problem. So I'm just going to take those values, and we get that V1 is equal to 0.861 meters cubed per kilogram. So we get that is U3 minus U2 plus H4 minus H3 plus, nope, sorry, that's supposed to be minus, not a plus, that's supposed to be a minus, minus U5 minus U1 all over specific rate volume of 1 times 1 minus 1 over R. So plug everything in. Get ready to write a bunch of stuff down. Okay, So this is going to be 1065 minus 673 plus 1778 minus 1452 minus 475 minus 214 all times 10 to the cubed Newton meters per 1 kilojoule times 1 megapascal per 10 to the 6 Newton meter squared, all over 0.861 times 1 minus 1 over 18. So the mean effective pressure is 0.56 megapascals. Whew, we did it! Go team! Alright, let's review. So, we were given a air standard dual cycle with a compression ratio of 18, standard temperature and pressure of the starting temperature and pressure of 300 Kelvin and 0.1 megapascals. We were given a pressure ratio for the isochloric section of 1.5 and a volume ratio for the isobaric section of 1.2, and a dual cycle. Oh, I'm sorry. The pressure ratio for the constant volume part of the heating process is 1.5, not just the pressure ratio for the isochloric part of it. It's the pressure ratio for the isochloric part of the heating process. My bad, I didn't write that down. I'm going to write that down right now. Heating process. Because you might have been asking, well, John, why did I just use that down there? That's why. It's for the heating process. And the same thing for the volume ratio for the constant pressure part of the heating process is that. That's why they were different. All right. I hope that alleviated some confusion. I'm very sorry for not writing in that part of the heating process. So we were tasked with finding the thermal efficiency and the mean effective pressure. Well, the thermal efficiency is based off of this equation here. Well, we need to know internal energies, and we need to know enthalpies, so we have to find those values by going and analyzing every single individual state point. Luckily, there's only 5. Wait till it gets to like 20. That's where the real fun begins. Had to solve one for a project. Took like 20 pages. It was not very fun. I mean, it was exceptionally fun. Not really. We analyzed each state point using the volume ratios for each state point and the ideal gas law, and then looking those specific temperatures up in the table to get our internal energies and enthalpies that we needed for each individual state point. Then we plugged them all into the thermal efficiency equation here. Plug and chug. Got 63.5%. Mean effective pressure, the specific volume at state point 1 is given here. And now it is given here because these values are the exact same values we used in the previous video, lesson 10, where we covered lesson 11, where we covered a diesel cycle. If you want to go to the last 3-4 minutes of that video, that covers how we got this specific volume. From that value, we plugged it into the mean effective pressure here, plugged in all our values, and we did some dimensional analysis to get it to megapascals. I hope you all found this video very useful in explaining how dual cycles work and how to analyze them. If it did, please leave a like and subscribe to these videos. If you have any questions, please leave a comment on the video and I will answer it as soon as I can. Thank you very much and have a wonderful